In this video, we will be talking about multi-step reaction energy profiles. As we've said previously, most reactions have multiple steps, and the rate of the reaction is determined by the slowest step. In a single-step reaction, you see a simple energy diagram like this one. But in a multi-step reaction, each elementary step has its own activated complex and its own activation energy barrier. The slow step has an activation energy barrier that is higher than the energy associated with the faster reaction. Let's take a look at this diagram. The first hump represents reaction 1, and the second hump represents reaction 2. And there's a little intermediate in the dip between them. The first reaction is the rate-limiting reaction, and we know this because the activation energy is larger than it is for reaction 2. Here's another more complicated multi-step reaction. In this reaction, there are 3 elementary reactions, and each of these is represented by a peak. And the top of each peak represents the potential energy of the transition state for that reaction. We can also see we have 2 intermediates, and they are located at the lowest potential energies after each reaction is done. Based on this diagram, we know that the rate-determining reaction is step 2, because the activation energy barrier is the highest here. From this picture, we know that reaction 1 and 2 are endothermic reactions. And we know this because the potential energy gets a little higher after each reaction is completed. Reaction 3 is exothermic, and we know this because the potential energy at the end of the reaction is much lower than it was at the beginning. The overall reaction is also exothermic because the potential energy of the products is lower than the potential energy of the reactants. A common type of question you might see on the AP exam is one like this, where you're given a reaction mechanism and you're asked to sketch a reaction profile for this mechanism. Well, let's take a close look at these 3 equations. We see that the first reaction is a slow one. This means it's the rate-limiting one, and this also means it's going to have the highest activation energy. We are also told that this reaction is exothermic, so we need to make sure that the potential energy of the products of this reaction is lower than the potential energy of the reactants. So we will draw our peak like this. It's going to be our tallest peak, and it's also going to be exothermic. Now let's take a look at the next peak. It's a fast reaction, and we know that it is also exothermic. So when we draw this, we need to make sure that the potential energy of the products is lower than the potential energy of the reactants that went into this reaction. We also need to make sure that the activation energy for this reaction is smaller than it was for the first reaction. Now, let's draw the final hump. We know that this reaction is going to be exothermic, so we want to make sure that our products are much lower in energy than our reactants were. We also know that it's a fast reaction, so we need to make sure that the activation energy is lower than it was for the first reaction. Now, this is not the only way you can draw this, but you need to make sure that reaction A has the highest activation energy and that all 3 reactions are exothermic. Let's summarize. Knowledge of the energetics of each elementary reaction in a mechanism allows for the construction of an energy profile for a multi-step reaction.